All right, this is going to be two videos in one, 4-5 solving equations graphically, and 4-6 just rules of functions. And this is really just one example to explain how we might be able to solve something. If we can't do it algebraically, we might be able to do it graphically. And this is where using a graphing calculator could come in very handy. Or a tool like Desmos, but you won't have a tool like Desmos on an exam. So let's talk about it. It says, can you solve the equation log base 2x plus 4 equals 3 minus x? Probably a little difficult. It would actually be very hard. I don't even know how we would do this, because every step we would take, we would still end up with x's on opposite sides. We wouldn't be able to get x all by itself. Or at least there'd be other stuff in there with the x. So what we could do is rewrite this equation as a system of two equations. So you have y equals log base 2x plus 4, and then y equals 3 minus x. And then we graph these things separately. So when we graph these separately, here's y equals 3 minus x, and here's the log function. And so the solution for x then must be this intersection point right here. And so if you use a graphing utility like Desmos or like a graphing calculator, and on the graphing calculator I'll actually show you guys how to find these intersection points. But if you use that, it can actually tell you these values. It can estimate them for you. And I had it just round to 2 decimals, and I got that this location is 0.75. This is approximately. I mean, these decimals go on forever. It's an irrational solution. And 2.25. So we can say then, what is the best approximation of the solution to the system where the two functions intersect? Well, we could say then that x is approximately 0.75. And even without a graphing utility, like if we had these graphs, we could still get a pretty good idea that, hey, you know, it's somewhere between 0 and 1. And it's a little bit closer to 1, so, you know, we could say about 0.75. It'd be a good approximation to say, like, oh, it's about 3/4 of the way. Or even if you said 0.7, right? That'd still be a good approximation. All right. So general method to solve an equation. We let y equal the expressions on both sides of the equal sign, graph them each separately on the same plane, and approximate the point where they intersect. That's all there really is to it. It's pretty straightforward. Okay, on to 4.6, rules of functions. Just some basic things that we want to learn or remember about some functions, okay? So first off, even functions are symmetrical about the y-axis. So what does that mean? That means like you got your graph and they're going to be even like this, right? So if you folded this over, if you folded this side over the y-axis, they would match up perfectly. And another way to kind of notate that is that f of negative x will be the same thing as f of positive x. Okay, so they have the same height. So if you go 5 over here, you're going to have the same height as you go 5 this way. Maybe I'll put like a comma there. Okay, odd functions are symmetrical about the origin. And algebraically, the way you could write this is that f of negative x will equal negative f of x. Okay, and so like a sketch of this for an odd function would be like a cube root is an odd function. Not a cube root, sorry, a cubic function. So as you go, let's say you go 5 over and you go up so many, you'd go 5 back and you'd have to go down so many, okay? So that's the basic layout of the rules for even and an odd function. Now, determining the x-intercepts. Well, let's talk about this. What is an x-intercept? Well, if we go back over to this graph, right, this is the x-axis. And the y value here, what do we know about this? Well, we know when the x-axis is when the y equals 0. So that's the first thing I'm just going to say. This is when the y, or the f of x, equals 0. So I'm going to replace the f of x with the 0. And then I'm just going to solve. So that's when they give us the function, we can just do that. We can solve. So I'm going to subtract 5, and then I would get negative 5 equals x squared, and then I could take the square root, and what do I notice right away? I'm going to have imaginary numbers, and so this one doesn't have any real x-intercepts. We might be able to find some imaginary ones, though. We could say that it has I square root 5 plus or minus, but no real intercepts. Okay. What about from a graph? Again, well, it's just all about when the y equals 0, right? Well, here's the y is 0, and so we can tell from this graph that we have a y-intercept at x equals -6. Okay, what about from a table? Well, in a table, again, we're just looking to see when is the y 0. And we have the y equals 0 here, and the y equals 0 here. And so therefore we must have x-intercepts at x equals -2 and +3. What about determining y-intercepts? Well, okay, let's just backtrack here a little bit. If the x-intercept is when the y is 0, well, the y-intercept is when the x is 0. So let's mark that. That's going to be at x equals 0. So algebraically then, I can just plug in a 0 for x and solve for the y. So 0 squared is obviously 0, 0 plus 5 is just 5, and so we have a y-intercept at 5. Over here, graphically, I could just say, okay, when does this thing intersect the y-axis? When is the x 0? And it's right there, and so we could say at y equals 2. And from a table, oh, interesting, this table isn't filled out for us, but it's when the x equals 0, and so if we had this table filled out, we would know that it must be right here. It would be whatever value you have right here, okay? So those are just some key things about functions that we want to keep in mind as you go through the last few skills and last few concepts of this chapter. All right, don't forget to write a question at the end of this video, and I'll see you guys on the next one.